Okay, so this is the problem that we're gonna solve in the classroom today. It's a little bit long, and so just keep track of what we're gonna try to do, and then you're gonna try to do homework. Just gonna be one problem due on Monday, and it's gonna be shorter than this. So if you can follow this one, you should be able to do the other one of the homework. So really quick. So we have a spring that is compressed. It's compressed 50 centimeters, and the spring constant is 250 newtons per meter. At the end of one of the spring, we have a block, and the block has a mass of 1 kilogram, and obviously the initial velocity is going to be 0 meters per second. After the spring is expanded, the mass is going to be moving along a rough patch, and this rough patch has a length of 1 meter, and we're going to have a friction coefficient of 0.1. And the end of that rough patch, then we're going to have a ramp. The ramp has an inclination of 20 degrees. We have a friction coefficient of 0.5. And what we want to find out is how long it travels along this ramp before it comes to a full stop. As you can imagine, this could be a similar example of a truck going to an emergency ramp out of the road. That's more or less what it's trying to do here. So, so to keep track of all the different parts, I'm just gonna name them. So this will be stage 1. This will be 2. This will be 3. And at the end, I'm gonna have 4. Okay. So this is a conservation of energy problem, and because we have these sections with friction, there's going to be a loss of thermal energy. So we're going to have, we cannot do that the energy of 1 is going to be equal to the energy of 2. It's not going to work because we lose energy along the way. So I'm going to have to do step by step. So I'm going to say that the energy at 1 is going to be equal to the energy at 2. And the energy at 1 is only going to be spring potential energy. So this will be spring potential energy. And it's going to be equals to kinetic energy. So at 2, before we go to the rough patch, we're only going to have kinetic energy. So we're going to have kinetic energy. Now be careful, this K is kinetic energy, this K is a spring constant. So here we're going to have 1/2 of K delta X square, the delta X at 1. So this is the how much the spring is compressed. It's going to be equals to 1/2 of the mass times the velocity at 2 square. So you can see that these are going to cancel. And then I'm going to have K delta X square equals mv2 square, and v2 square is going to be K over m delta X square. So v2 will be K over m square root of this times delta X. So this will be 250 or 0.50 square. No, the mass is 1 kilogram, sorry. The mass is 1 kilogram times 0.5. So this will give you 7.9 meters per second. So this is the velocity at 2. Okay, so now we need to do from point 2 to point 3. So the energy at 2 has to be equal to the energy at 3. So the energy at 2 is going to be kinetic energy. So we're going to have 1/2 of the mass v2 square. And the energy at 3 is also going to be kinetic energy. But we're also going to have thermal energy. Okay, the thermal energy is going to be mu k times the normal force times delta x. And this will be mu k. And because we're in a flat surface, so you can imagine that we have gravity, and we're going to have the normal force. So the normal force here is going to be equals to mass times gravity. So this will be mg delta x. Okay, and again, we're solving for V3. So we're going to have, I'm going to write it all here. And I'm solving for this guy. So I'm going to have, this is V2 minus this, mu k mg delta x equals 1/2 of m V3 squared. And I'm going to multiply everything by 2, and I'm going to flip this. So if I multiply everything by 2, I'm going to have mv3 squared equals mv2 squared minus 2 mu k sorry, we have mu k mg delta x. Okay, I can get rid of the masses, so I've divided everything by the mass, and obviously I will need to take the square root. Okay, and then I can substitute values. So here will be 7.9 squared minus 2 times 0.1 times 9.8 times 1 meter. Square root of all that. And this will give me 7.78 meters per second. So just a small reduction in the velocity. Okay, now I'm going to do between 3 and 4. So I'm going to redraw this part in the next page. So I'm going to have this. So this is 0.3 and this is 0.4. This is delta x. That's what I want to find out. I know that this is going to be 20 degrees, and I know that mu k is going to be, I forgot, so let me double check. Mu k is going to be 0.5. It's getting out of focus. There you go. Mu 5. Okay. So again, we're going to have that the energy of 3. This is the tricky part. This section between 3 and 4. So energy between 3 has to be equal to the energy at 4. At the bottom of 4, at the bottom of 3, so here where the box is here, we only have kinetic energy. The thermal energy got lost, so we don't care about that one. So here we have kinetic energy. We're going to have kinetic energy at 0.3. And at 0.4, we're going to have gravitational potential energy. Okay, and we're going to have thermal energy. Okay, we're assuming that here the velocity at 4 is going to be 0, so we lose all the kinetic energy. We want to find out the maximum height. Okay, so we're going to have kinetic energy. Sorry, we're going to have gravitational potential energy, and here again we're going to have mu k times the normal force times delta x, and this is what we want to find out. Okay, now a couple of things. We need to find out what is the normal force, and also we have this other variable, the height, which is kind of annoying, and so we need to find a way to get rid of it. I'm going to work with the normal force first. So I'm going to have my block going up. This is 20 degrees. I have gravity pulling down. I have the normal force going like this. Okay, so I'm going to have my frame of reference, which is going to be like this. This is going to be theta, so this is going to be 20 degrees. And then I'm going to have the normal force minus mg cosine of theta is going to be equal to 0. You can imagine that there's a friction force here. So the normal force is going to be equal to mg cosine of theta. Okay, so mg h IV. So we have here the gravitational potential energy plus mu k mg cosine of theta delta x. Okay, so I have this expression. This is what I want to find out. Now I need to find a way of get rid of this because we don't know the height. Okay, so for that one, I'm going to use a little bit of trigonometry. So my ramp and delta x, whatever delta x is going to be related to this height because they're part of a triangle rectangle. So this is going to be theta. And I know that sine of theta is going to be equals to opposite over hypotenuse. So h over delta x. So I can rewrite and say, well, h, this height, is going to be equals to delta x sine of theta. Okay, so I can rewrite my gravitational potential energy as mg delta x sine of theta, and this expression over here represent this h. Okay, and then I can write the rest nk mg cosine of theta delta x. And now you can see that I have, okay, the kinetic energy at point 3 has to be equals to all these, and now I only have one variable, which is great. So I'm going to factor out that variable. So I'm going to have delta x times mg sine of theta plus mu k mg cosine of theta, and that's it. Okay, and kinetic energy at point 3, this is going to be 1/2 of the mass times the velocity 3 squared. Okay, so now I can solve for delta x. Delta x is going to be this huge expression, mb3 squared over 2 times mg sine of theta plus mu k mg cosine of theta. The masses going to cancel. Okay, remember you want to cancel numerator and denominator. For example, the m has to be in all components. If you only have one variable m and 2 of them, but you don't have on the third one, you cannot cancel. Okay, so we got that, and now we can substitute some values. So here we have 7.78 meters squared. 2. You can also factor out the g. So, but I'm going to leave it like that. Sine of 20 plus mu k 0.5 9.8 cosine of 20. And then we can find the solution. We can find a numerical value. So 7.78 square, and then whoops. Really? I got 39.8 meters, which is huge. Maybe I did something wrong. Oh no, that's a factor. I got 3.8 meters. There you go. Okay, I hope this makes sense. I think the first two parts are quite, you shouldn't have a problem with those. So I hope you don't have any problems. This is the part that is kind of confusing. And the main problem is how do we get rid of this height? Or how do we express this height in terms of the length of the hypotenuse? And you can imagine that it can be the other way around. I can give you this length and I will ask you for the height and so on. So take a look at this, repeat the video as many times as you want. There's going to be a small homework that is going to be somehow similar to this. Okay. Now I need to stop this video.